Hello, everyone. My name is Damani Cephas, and I'll be introducing the Analyzing Biological Networks project, or CyFinder for short. Um, Inside this project, we have a plugin that we created called CyFinder, in which we put into the Cytoscope program. This plugin is what we would be using to actually implement algorithms and create connections or communities for these networks. Cytoscope itself is only a visualization tool for visualizing complex molecular networks. Um, in the next image, we are going to be seeing a UI breakdown. After importing CyFinder into Cytoscape, it gets added to the apps dropdown, and as you can see here in the community detections, it adds the algorithms that we created. uh Three of them here are from the prior class and label propagation, as you can see. So this is an example of the process of adding the new algorithms to a UI. Inside of this project, we have two separate, I guess, projects, programs. The first one is Subgraph Finder, which is the logic, where we have like graphs, everything that works and goes on in the backend to create the communities and the connections and find those similarities and everything that's going on. And then we have SciFinder, which is the UI portions, and we have to create a connection between these to be able to get it to work properly inside of Cytoscape. We also expand a little further on an external functionalities by implementing or further expanding on the command line interface tool, which was started by our prior class, but we were going to add other algorithms to that. And going forward with that, we have a few functionality that's already inside of Subgraph Finder: Kruskall's algorithms, and Prime's algorithm, which are spanning forest algorithms. Those were added before us. Community detection algorithms, we have three that were added before us: Edge Betweenest, Fast Greedy, and Walk Trap. And then the two that we added: label propagation and leading eigenvector. So to expand further on this, I'm going to be passing it on to Gabriel.
Hello, everyone. So continuing from where the money left off, I'm going to talk a bit more about the command line interface tool. So now, originally, this was a part of the first build of the project, in which this command line tool allows the user to run the algorithms of the program directly from the command prompt. The first build of the command line interface only included the first two backfinding algorithms that you saw on the previous slide. And ever since then, they haven't updated it yet. This semester, our group expanded on this, in which we added new clustering algorithms made by both our group this semester, as well as algorithms made before by previous groups in this project. And the fun fact about that is this. This project itself is just focused on biological networks. The algorithms that we use can be applied to pretty much anything: social, technology, information-based networks, anything. Um, and while possibly these algorithms have been enabled by the rise of computing technology, as well as performing these algorithms manually require increasing levels of computation complexity. Moving on to the next slide, you can see a few examples of our community detection algorithms visually. And now I'm passing on to Adam.
Alrighty, so the first algorithm that we are going to be going over is label propagation. In front of you, you're going to be able to see the mathematical definition that we found via a research paper. This algorithm is broken down into 4 steps. This is more of a in-depth explanation of it. And so the way that this is functioning is that first, all the nodes within any given network are assigned to its own unique community. So for any node X, it is placed within community X. And then all of those nodes are assigned within a random order, and that random order is big X. After we have this random order, we go through each node, little x, within big X, and we take that and we are looking for this function that is explained under step 3. is essentially looking for the greatest represented community surrounding its neighbors, which I will explain further in the next slide. But we are trying to see for each iteration what community label each node would take on. And then the final step is essentially to see if all of the nodes have the label that was present in the previous iteration. If so, the algorithm stops running. So here's a simplified explanation as I was going through. Each node is given its own unique community, and once again, this will be visualized in the next slide. So for each node, let's just imagine nodes 1 through n, they would have labels 1 through n. And then we assign a random order for those nodes. And so this is important because this algorithm is non-deterministic, meaning if we run this algorithm multiple times, although we would get similar communities just based on the structure of the network, it does not mean that the labels of the communities will be the same, although these labels are arbitrary. Then third, for each node X within its community, we check all of the labels surrounding or connected to an individual node, and we find the most represented node, and that's taking into account both the weight and direction of the graph. And then finally, as explained, once we reach an iteration that is the same as the previous, we know we have reached the end of the algorithm. So just to visualize that process a little more, first we talk about how each node is given its own unique label. In the program itself, this is functioning numerically with each node getting label 1, 2, 3, so on and so forth, all the way to n. But here we visualized it using colors. So each node would have its own community at the beginning. And through each iteration, so in the middle you would see an example iteration of label propagation, we can see how, for example, the yellow node was assigned, or the yellow community was assigned to many of the nodes around it as the label propagates throughout the graph. This continues until we eventually reach a point at the end where the different communities or clusters are separated, and you can actually see almost at the beginning of the graph how these clusters eventually form due to the inherent structure of the graph. So that one single edge between the two middle nodes, the yellow and the blue node on our last iteration, that's kind of where you would expect to see the end of one community and the start of another because the nodes are not deeply interconnected. So now we are going to move into a demo of our program. So here we can let's first remove this old run. And first thing we do is we import a network here. And I'll minimize that so we can see the full program. And we'll first import a network. BRCA is one of the important networks we've been testing on this semester. This is representative of a real-life cancer network. And as we load the network into the table, we can see this is the full mapping of the BRCA network. You can see all the various nodes and the connections. And so now we will run the label propagation algorithm. So as Damani explained, we go to Apps and CyFinder. This is where our program is located. And within community detection, we have our label propagation algorithm that we've made. What we're able to do is we can change the minimum node count for the represented graphs. This is important. I will go back and show in a minute. The minimum node count, there might be small connections with only 2 nodes, so we want to set that to a higher number. And we're going to save all our corresponding clusters in descending node count order. So now the algorithm takes a little bit to run. And after it runs, we can create these views of the different networks that are created, or the different clusters that are created from our original BRCA network. Now, just to go back, as I was explaining before, there's a couple of the genes are mapped just 1-to-1 down here, which is why we increase the minimum node count, because these would all represent as their own clusters as they're not connected to the rest of the network. But for the rest of them, we end up getting these complex little clusters that have biological significance for researchers, and this is the primary function of our program. So this is the demo of label propagation. So now I'm going to hand it off to my teammate Steven, and he's going to explain a little bit about the leading eigenvector algorithm.
Hello, and yes, I'm going to be introducing the leading eigenvector portion. I'm going to be parsing the mathematical definition into the computational, where we start off by first grabbing to get the eigenvectors first and foremost, we have to get the adjacency lists of all the nodes involved in the program. transfer them into an adjacency matrix, transform that into a degree matrix, and then subtract the two from each other to get what's called the graph Laplacian. And then passing that graph Laplacian into a power iteration method, we can calculate the eigenvectors. And we grab the first non-zero eigenvalue and get the eigenvector from that. And then we will get two sets, A and B, arbitrary for now, that will be created inside this subgraph. Then, according to the values of that eigenvector, every row will match the number of that node assigned to in the matrix. And according to whether that value is positive or negative, it will be partitioned into two sets. Into set A if it's above 0, and into B if it's below 0. So if it's a negative double, it'll be partitioned into A, and if it's a positive, it'll be partitioned into B, or vice versa. On to the next slide, into the visualization. Yep. Here we see the Fiedler vector, as it's called, and it is the representation of how we would be seeing the partitioning, with every row coinciding with the number on the of the node. And now we will be going into a partial demo of the leading eigenvector of the work we have done so far. We have been able to create the graph Laplacian and the adjacency matrix and all that, and the processes to get there. And this is going to be a visualization of that, passing into the command line, which is a massive graph that we cannot fit into this, of approximately 560 nodes. So it's a 560 by 560 matrix. However, passing this into the current method that we have, we do run into an error that will be addressed in later versions. Now, with that, I will be passing it on to Gersan, who will talk about the command line interface.
Okay, so in addition to these new algorithms that were added, Capstone 1 was working on expanding the command line interface functionality. They added flags in order to support the different parameters that the newly supported algorithms had. And the support for 4 algorithms was added, which were the fast greedy algorithm, walk trap algorithm, Braun-Kerbosch algorithm, and Prim's algorithm. And now Tyler, our Cap1 team member, will demo the functionality for the command line interface.
So here, Tyler is one of our Cap 1 members, so I, Adam, am going to just introduce this part. Here you can see this is from our command line tool that the Cap 1 students have built for us. It's at the top, you can see the input that Tyler was able to give to the command line. We select the jar file, as Damani explained, comes from our subgraph project, and the different various flags that he would need. These are similar to the options we saw in the Cytoscape program for running the other algorithms. Each algorithm will have its own parameters and options to it. And then what this allows a researcher to do is, instead of clicking through manually to, if they want to run an algorithm on a graph 100 times, this allows them to do it through a command line, so something that can be scripted, and so they can run the same algorithm, let's say 100, 500 times. And as you see at the bottom here, the output graphs are written to an output file, and so the researcher is then able to review those for whatever purposes he or she may want. So now we're going to continue back to the PowerPoint for Gersan to wrap this up for us.
So in conclusion, CyFinder, when we picked it up, was only able to perform 3 of 9 available community detection algorithms, but now there is support for 5, and this semester has also expanded on the development of the command line functionality, which also has new support for 4 new algorithms. And to contact the project owner, his email is at the bottom of the screen. And now if there's any questions that the crowd might have, the Q&A session is starting.
Thank you, and that is it for our demo today.